Good. Well, I usually try to comfort you guys as much as I can, although oh, we lost Dan. I did want to spend because of the situations going on, I wanted to talk a little bit about nuclear weapons and what to do if there is a nuclear blast. So though normally, I'm sending you pictures of like animals telling you everything's okay. And I mean, as of right now, everything is okay. But I wanted to show you this. So if you have any questions, I started grad school as a nuclear scientist, so I know a little bit about this stuff. But so this chart here shows the dosage versus time. And there's something called the law of 7/10s. So and it goes well, and the idea is that for every 7 hours raised to a power, the radiation decreases by a factor of 10 to that power. So meaning if you look at this graph, 1 hour after a nuclear blast, the radiation rate can be as high as 1,000 roentgens per hour, or what's it, rem per hour. So for dosage, if you are hit with radiation, you want to stay under 100 rems. So 100 rems is what will give you radiation sickness. And radiation sickness is like having COVID or having a bad flu. So you have a lot of similar symptoms. It's gonna be hard to breathe, you're gonna feel really weak, and you're probably gonna have skin lesions. You'll probably survive radiation sickness. So, but it's not, you're not gonna be very useful for a bit. So, and after, so 100 rems will give you radiation sickness, 60 rems will give you, make your hair fall out. And you won't notice anything in your body till you reach about 20 rem, 25 rem. So we're allowed, like in the United States, you're allowed to get 5 rem of radiation. That's your permitted radiation. If you go take class and get a permit, you can have 10. So, and you won't even notice till around 20-25 rem. Around that range, your white blood cell count starts to change. So usually it goes down, makes you more susceptible to infection after about that. And so at 60 rem-ish, your hair starts to fall out. 100 rem, you get full-blown radiation sickness. 200 rem and above, you're probably gonna die. So, and so with 1,000 rem per hour, so after a nuclear bomb, so as far as weapons, they're very, very dangerous, very powerful. But if you're depends on how big the bomb is, but if you're about 10 miles away from the blast, you're probably going to survive. So, which also makes us very safe here on Maui, right? Because what are they going to hit? They're going to hit Oahu, right? Pearl Harbor will hit them right there, Schofield Airfield in the center of the island. So those, Marine Corps Bay, Kaneohe Bay, those are going to be the targets. So also Barking Sands and Kauai, that'll be the main target. There's nothing here. The most valuable military target would be the satellite tracking station on Haleakala, right? So, but you don't need a nuclear bomb to take that out. You can do that with a cruise missile. Nukes are expensive. So, it would be a waste of a nuclear weapon to hit out a satellite tracking station. So we're probably safe here, but what we get hit with is maybe fallout. So, okay, so hour after the detonation, 1,000 rem an hour. So that means in 10 minutes, if you're outside, if you're exposed to that for 10 minutes, you're gonna get radiation sickness, right? So, and you'll feel the effects after 2.5 minutes from the radiation. So 25 rem, so 2.5 minutes. you'll start to have physiological effects to the radiation. So the point is, after a nuclear blast, you get into a shelter as fast as you can. And for shelters, the key is matter. It's more material and less ventilation. So for us, my plan is if we get a nuclear alert, we're going to go into the astrolab, because that's in the center of the building, and we're all going to lie down and, oh, the other thing is, if there's a nuclear blast, so let's say that a blast goes, and this works for any blast, keep your mouth open. So if you're somewhere and they say duck and cover, try and find a ditch or a wall and kind of get close to that, and also lie down and you're supposed to turn your face towards the blast and keep your mouth open. It's more important you keep your mouth open. The reason is because when the shock wave comes, if you keep your mouth open, it won't rupture your eardrums. Okay, so, but the other key is matter. Get as much matter as you can, into a ditch, by a hill. And the other thing, if you're close to the ground, when fluid flow happens, when it's close to the ground, you have what's called laminar flow. You're not going to have as much turbulent flow, and that means that the pressure wave and the force in general is just going to be much less the closer you are to the ground. So, and again, this works for any blast. So if the gas tank outside explodes, drop to the ground, keep your mouth open, and then it'll affect you the least. But of course, nuclear bomb's a big bomb. Okay, so, but then seek shelter as much as you can. And it's the most central. A basement is the best. Of course, we don't have basements here in Hawaii, but the most central area. So center hallway, room, or if you're in a room close to the door kind of thing. So if we were stuck in this room, the back wall there, I would have us kind of huddle towards that, for the most central area. And also less ventilation, like close your windows, turn off the AC. If there's electricity, turn off the AC. So, but okay, but then for the fallout, so it's very imperative that if there's a fallout, you get inside as soon as you can. And the most critical portion is the first 7 hours. So like I said, in 2.5 minutes, you can get a physiologically noticeable dose. In 110 minutes, you'll get radiation sickness. In 20 minutes, you'll get a lethal dose. So you stay inside. Question? When I'm sure you've seen like a nuclear bomb going, as the mushroom cloud goes off, and so you have the initial blast. So it depends. The way for nuclear weapons to be effective, it's better if they're called an air burst. So they explode in the air, and there's a couple things that happen. Initially, you get radiation in terms of gamma radiation coming off, and then you get a pressure wave. So that's just then that's where most of the damage comes from, the pressure wave. And then you have this big fireball that comes down, and then you have thermal, like heat damages from the fireball. Besides that, you also have a phenomenon called an electromagnetic pulse that just destroys all electronics. So, so you have that happens all really fast. And all those three things, the pressure wave, depending on where you're at, maybe a couple seconds though. I mean, within 10 seconds, that's all going to happen. So it's like if a blast goes off, you duck and cover as fast as you can, and keep your mouth open. It'll be over fast. Then you have this big cloud that comes up, and you have the radioactive particles made from the bomb. So that's the fallout, and it goes up, it shoots up really high, and then it falls back down. So that's the fallout. And here in Hawaii, it would probably seed rain. So which is a good thing. Well, it's good or bad. It's going to concentrate the radiation in a really close area, but it's also going to prevent the spread. So, but because of the winds, if the winds, depending on the way the winds are blowing, they could blow here. And so, which is, it's still going to take some time. I mean, the nice thing is like, probably take, like if they hit Oahu, it would probably take, 2-3 hours at the fastest, more likely 5 to 7 hours to get here. But still, if there's a bomb that goes off, you should get inside. And so the first 7 hour, yeah, question? It's going to be decaying. And it decays, in generally speaking, by the law called law of 7/10. So if it takes 7 hours to get here, then it's going to be 1/10 of as intense. And that's where the first 7 hours are very critical. So, and oh, by the way, the clock starts over every time there's a new bomb that goes off. Right. So one thing about nuclear weapons is you also seek shelter because there could be another one coming. So Russia has around 2,000 nuclear weapons deployed. So, that's a lot of nukes. So, there could be 3-4 coming and they could be 10 minutes apart. So, but yeah, so, and so the first 7 hours goes on to 1/10, and then, so 7 squared is 49 hours. And then that's 10 squared. So 7 squared, 49, 10, 1 over 10 squared, 1/100th. So I'm sorry. Well, yeah, 1/100th. So after 49 hours, 2 days. So after 2 days, the radiation goes down to 1/100th. But at the same time, so after you reach the first 7 hours, whereas you would get, you get a lethal dose in 10 minutes, or radiation, like a radiation sickness dose in 10 minutes, it would take 10 hours now. So, and no, it would be 10 minutes, it would be 100 minutes, so that'd be 2 hours. A little less than two, so I'm sorry. It would be 1 hour and 40 minutes, 100 minutes for radiation sickness. So that's still a lot of radiation, right? So you stay inside. So so the first 7 hours, you do not move, you hide, you just try and go to sleep, stay as low energy. The 2 days after, you hide in your house, because there's no shelters here. You hide in your shelter and do not seek food or water for the first 2 days. So especially the first 7 hours, the first 2 days, you hide and you stay as calm and as low energy as you can. After 2 days, though, you're at 1/100th. And so this is much, much less. So let's see here. So it'd be, instead of 100 minutes, it'd be 1,000 minutes, right? So to get a radiation sickness, but you also don't know what your exposure was while you were in the first 100 or first 48 hours, first 2 days. So after 2 days, so 7 cubed hours is about 2 weeks. You're free to move around after 2 days, but this is not the time to go to the beach. You should stay at home, and it's okay to go out, but for 2 weeks, up to 2 weeks after the blast, you should stay inside, but it's okay to go outside to look for food and water. This is when you go to Foodland and, start grabbing Gatorade bottles and that kind of stuff, or going to wherever, Memorial Stadium, and getting stuff, wherever they're having, and especially if your car works. So the car might work here because we're far enough. There's a lot of material between here and Oahu. So your car might still work. So you might still have electricity, but then it's free to move around in 2 days. But I'm just telling you this because, and I'm sorry if I'm freaking anybody out. It's just, I'd rather have you guys have the knowledge, understand what it means. So in case, because this is escalating fast. So some of the good old Cold War things. Anybody have any other question? Please ask a question. Yeah, go ahead, Dennis. It's, I mean, the answer is it depends. And the best answer I can give though is it is larger than the initial blast because, for instance, you can detonate a nuclear device either in space or in the upper atmosphere, and the EMP will travel further. Electromagnetic pulse EMP will travel further, and it'll knock out more things than and then and if you detonate something high in the atmosphere, it's not going to cause any destruction. Might cause fallout, but it won't cause any destruction. And also the fallout will be more diffuse if you detonate it up high. But the electromagnetic pulse, that's one of the dangerous situations, because you could if say that a nuclear device was detonated in the stratosphere above Oahu, the entire state of Hawaii would be wiped out electronically. So no electricity. We have some things that would work, but I mean, cochlear ear transplants, pacemakers, they'll stop functioning. So it would kill the pacemaker, but maybe not the ear transplants, but then yeah, computers, electricity, everything would be fried. Televisions would no longer be working. And same thing with the US mainland. If they detonated some bombs over that, you could knock out most electronic systems in the country. So, and cause no damage, or at least no like, classical pressure force damage. So does that answer your question? But I mean, I'm saying it depends because it still travels in a straight line. And, if you're, like, depending on the context, I mean, if you if you're shielded, then yeah, it's not going to affect you. How do you shield for an electromagnetic pulse? A Faraday cage. So Faraday, like a strong enough Faraday cage, just a metals, just a conductor surrounded something. So, and depending on the size of the pulse, you need more conductors. I mean, you could Dr. Rye, has a Faraday cage in his lab. It's like a big metal bird cage, and he can take whatever that machine is called. I forget the name of it, but he shoots lightning bolts, and I think he does that where he sits in a wooden chair in the cage and he's getting hit by lightning bolts from this thing. He's like, I'm fine, kind of thing. So I'm in a Faraday cage. So, and your car is a Faraday cage. And, if a lightning bolt strikes your car, as long as it doesn't hit the fuel tank, you're pretty safe in your car because of the metal frame of the car. It's a Faraday cage. That's a nuclear weapon is going to overpower that Faraday cage. So it's not, I mean, it's going to fry your engine, or at least the electronics that control your engine. So that's not, it just depends on your shielding, depends on distance, and distance, it's 1/r² for distance. So, I mean, it's not like, one EMP is going to knock out absolutely everything all around the world. No, it depends on how much shielding, how much distance, and these type of things. But it's not a good scenario. We're very vulnerable that way. That's why, even though the war is not going very well for Putin and Ukraine, he can still cause a lot of damage with his nukes. So
what about like what else called radiation bills? That work?
So if you're given radiation pills, what those are, that's potassium iodide. So I even wonder how much this works. So one of the products after a nuclear blast is iodine 131. So it's a radioactive form of iodine, and your thyroid gland here, it soaks up iodine. So the idea though is if you You take the potassium iodide, it saturates your thyroid gland with iodine. Nothing else can be uptaken. So it really protects your thyroid gland. So a couple things of that. The dosage of the radiation pills is enough that it doesn't give you a condition called iodism. If you take too much iodine, you get a condition called iodism, which makes you sluggish, and it's unhealthy. It's not toxic. It's not lethal, but it's toxic. It's a toxicity, and it gives you a condition called iodism. Too little, and you get something called goiter, where your thyroid gland expands and your metabolism goes down. So it's an old moderation argument. Too little is bad, too much is bad. So for me, myself, if there was a nuclear bomb and they had me the pills, I would take them. But at the same time, we live in the United States, and we enrich our food with iodine. So we put it in our salt. If you drink milk, if you eat bread, if you put salt on things, if you go to any fast food restaurant, we have tons of iodine in our thyroid. So that's one thing about the United States, is that we have very few nutritional deficiencies. I mean, we have the obesity problem, but you do not typically see people with deficiencies of calcium, iodine, vitamin D, vitamin Bs. So these types of things typically don't happen in this country. Under Soviet rule, they didn't enrich their food. And a lot of the people there, they had some iodine deficiency issues. So when the Chernobyl event happened in 1986, a lot of people ended up having thyroid issues because of the uptake of radioactive iodine into their thyroid glands. So, I mean, it's one of those risk versus reward arguments. So if you ever know anyone who gets the iodine 131 treatment, you have to go on a special diet before you get the treatment, where you can't take anything with salt. You can do kosher salt, but not normal salt. You're eating fruit and meat, basically. Nothing dairy, no dairy, just fruit and meat for like a week or two, so you can clear out all the iodine from your system, so that way it uptakes it easily. So in a way, I mean, like I said, even if you don't get the pills, you're probably, at least here in the United States, you're pretty safe. And we also eat a lot of seafood here. There's iodine in seafood. So, and some, like I mean, I'm Catholic and Lent's coming up, and one of the Catholic rules is to eat fish on Fridays during Lent. It used to be fish every Friday, but the original rule, they believe it came from iodine. They noticed that, oh, you need to eat fish once a day, and like, okay, I know, Friday, you must eat fish on Friday. So a lot of the religious rules actually do have whatever nutritional value to them. So same thing with Jewish and kosher laws and halal laws for Muslims. Can't eat pork, for instance, and there's trichinosis in pigs. So that's one way to avoid people getting that specific disease is not letting anyone eat pigs. So anyways, so it's not just Catholics. But other questions?
When I talked about like cyber attacks and stuff, what is this stuff?
So what is a cyber attack? So this is not my area of expertise. So what it looks like some of the major things are, there's a denial of service is a common one. So where people and actually Anonymous is doing this right now to Russia. They're doing refusal service. They basically just try to repetitively log into something, and then websites don't work. So like a lot of the websites, anything that requires a login, banks, Facebook, email, they're always being logged in, and like it overloads the system. So then they just don't work at all, kind of thing. So a lot of websites get shut down that way. And you can do so the more advanced things, there's computers that control many things like traffic lights and air traffic control and things like this that you can, advanced forms of cyber attacks can get into those and disrupt that. And like also other infrastructure things like water and electricity, they can If these systems are not isolated, some of them are, but those tend to be more the military ones. But the civilian ones tend not to be. They can they're susceptible to these, and they can, with cyber, different types of cyber attacks, they can knock out those things. Again, though, this is not my area of expertise, so my knowledge of this is only surface level. So, although we were, if you've noticed that I had to update all my electronics recently because they're afraid of cyber attacks from Russia. Actually, have you noticed that? Well, at least I have my iPad and my MacBook Pro right after whatever Ukraine war, like, oh, we have all these updates for you. It's because of cyber attacks. Yeah, Dennis.
Why did it take so long to, like, when Chernobyl was into the long radiation?
So it depends on, well, Chernobyl, like, it's well, okay. Let me think how to talk about this. So if you look at a nuclear bomb, so a small, like a normal size nuclear bomb, like a plutonium bomb, has 10 kilograms of radioactive material. So the critical mass for plutonium is 10 kilograms. That's about the size of a softball. So you need about this much nuclear material to make an atomic bomb. So with plutonium, it's 50 kilograms for uranium, which is, if you, like, if this backpack was all uranium, it would be, about that much. So, and you compare it to a nuclear power plant, and the Chernobyl nuclear power plant was, it was on the order of like a couple gigawatts, and which means the core, there was a couple cores, couple times the size of this room. Okay, so that's a lot, and that's so also a difference between a nuclear device. And they enrich uranium to somewhere between 3 and 9% fissile material. They to 235. You need an odd number. So we typically enrich to 3 to 9%. A nuclear bomb, it's almost 100%. Beyond 20% is called ultra enriched. So we have uranium, and it also transmutates plutonium. So you have uranium and plutonium, on the order of 10-ish%, 5 to 10-ish% radioactive fuel, and you have a huge area of it. And so there's just a lot more, like, in terms of, nuclear weapons that are kind of small, compact, and they give off their radiation immediately. So like the blasts last, the nuclear reactions that are involved, they're not going to take longer than a second. So whereas a nuclear power plant is continually doing that, and just the huge volume and amount of mass of that they have, and Chernobyl was exposed to the air. So, and it was an active nuclear plant. It was an active nuclear reaction going on with no shielding, with no containment, and that was going on for days. So where a nuclear bomb, like I said, one shot, though it's a huge amount of radiation, but it's like a second long, versus days of open releasing to the atmosphere. And then because of all that radioactive material, when it spread around the area, and it's and some of it releases quickly, so other takes a long time. So strontium 90 and cesium 131, those have half-lives, so take half to go away. We talk about half-lives of about 30 years. So that area is going to be hot for about 30 years, or not 30, it'd be about a couple hundred years. So like 200 years or so, it'll be pretty uninhabitable. But Chernobyl was terrible, absolutely terrible. I mean, it's about as bad as it could go. But like, if you look at the other nuclear accidents that happened, we had 3 Mile Island in the United States. Actually, almost everything was contained. Horrible, expensive cleanup, but we didn't have very much radiation released. There was the Fukushima event in Japan. And actually, I mean, there's some of the surrounding area is pretty bad, but it's not as nearly as bad as Chernobyl, not even close. I mean, so if you remember, there were the plant workers like, we're staying here, and they were actually pretty safe. They had they call themselves a samurai, and they actually hit 25 rem of radiation, and I mean, after that, they're going to be a little more susceptible to cancer, a little more susceptible to infection. So I mean, their hair shouldn't fall out with the amount of radiation the plant workers got in Fukushima, even though they were sleeping in the plant, you know, trying to keep it going and preventing things to happen. I mean, that's very different than Chernobyl, where you had thousands of people that were cleaning up and died from acute radiation sickness, you know, days to weeks after the event. So much, much worse. So, other questions?
I guess like how would you measure
How much radiation?
the count?
Oh yeah, of course. Yeah, Geiger counter. It would be just there's a couple different ways to measure radiation. I was talking to a student earlier. The student was talking about film badges. You can have a film badge. Maybe you've seen it. They're called dosimeters. They're about this big, and you typically wear them on your chest or on your hip. And they're film, and they, depending on the exposure of the film, it says your dosage. That's one way to do it. Another way is something called a scintillation counter. It uses material like cesium iodide, and when radiation passes through that, it generates light. You can detect the light. You either do it at a long exposure, or you can do it digitally. That's another way to do it. And the more common way, besides a film badges are so cheap. It's a Geiger counter. A Geiger counter is a tube that has a wire in it. Usually has argon gas in the tube, and then when the radiation hits the argon, if it ionizes, if it causes damage, it'll send an ion to the wire, and you detect the current that goes to the wire from the ions hitting it. And that's, each one of those is a click. Maybe you heard a click, 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 click. That's when the ions hit the argon ions hit the wire, and it registers that. So you can register it that way, and then it's calibrated such that, like, I think it's around it detects maybe 1 out of every 10,000 events. So then it tells you the dosage from that. So those are the 3 principal ways to detect radiation. And I mean, we have a Geiger counter in the library. It's one of the big yellow bricks. You've seen it. Be careful. I have one, and I actually I keep it in a safe, because if a nuclear bomb does go off, the safe will shield it from the EMP, so my Geiger counter will still work. So I'm a little bit of a doomsday prepper, maybe not a medium-sized one. So, but I have a plan for if there is a nuclear event. So my plan is to spend 2 days, well, depending on, because assuming my Geiger counter works, I'll be able to figure out what the radiation dosage is. But my plan, if the alarm sirens go off, I'm gonna go. I call it my Harry Potter closet. It's a closet underneath my stairs, and that's the most central room in my house. I'll just go there, you know, lie down and make sure all my windows are closed, and wait till the bombs go off or all clear. So, you know, even after you have one go off, you know, wait a little bit, because there could be more coming. And then I'll go and you know, make sure all my windows are closed. Then I'll sweep for radiation. I have duct tape. I have plastic bags. If I depending on if like a window blows out or windows blow out, I'll cover them with the plastic sheeting and duct tape. And then I'll either shut off, like I'll try and stay central to my house as long as I can, at least 2 days. If the radiation level is low enough, I'll stay in my house, but I'd go around my areas of my house. But then after 2 days, then I can, kind of reassess the situation. But to be honest with you, if someone's saying we're evacuated now and it was under 2 days, I wouldn't leave my house. I'd be like, oh, you guys go ahead. I'm staying here. Because if you go outside, you're going to hit with radiation. So, but that's just me, myself. But then again, I don't know if someone's saying we're being targeted, then I'd be like, okay, well, maybe I will leave. So, other questions? Yeah, Dennis. I'm sorry, can you say one more time? Okay. Is there a special material that's really resistant to radiation? The answer is just matter is in general. So if you are behind, if you're behind a foot of lead, that tends to stop almost everything. And also about 10 feet of concrete will also do it. So that will almost stop all radiation, at least from a nuclear blast, and also nuclear power plants. So it's not any special type of material. It's just more material. So, and it's more matter, and it's also the other thing is the intensity of any radiation. This includes everything, sound, although that's not radiation, light, gamma. It's 1/r squared. If you double the distance, you drop the intensity by a factor of 4. You triple the distance, it goes by 1/8, and so on. So distance and more material. But then again, with a fallout though, you can also be breathing in gaseous materials. So that's where you want to have a low ventilation. So it's not the time to turn on the fans. If you have electricity in your house, keep your AC off, keep your windows shut, don't turn on your fans. Just drink a few more bottled water and lie low. So other questions? I do have something comforting to say, and I'm gonna. Okay, I can talk about this. If you look at the amount of energy that's released in a nuclear explosion, it's nothing compared to normal events. Like an earthquake, like a magnitude 6.0 earthquake is bigger than the entire nuclear stockpile of the Earth. The amount of energy that's released in that. So is this going to be the end of the world if we have a huge nuclear exchange? It might be the end of humanity. Probably not. But the thing is, all at the same time, probably not, because enough people would take shelter, kind of thing. But it would cause major problems. Most electronics would be fried, and then there's going to be famine, after a huge nuclear exchange, and it's not something we say, oh, we should, this is something cool, but no, it's not, but it's literally not the end of the world, kind of thing. So, and I don't remember, I'm not going to repeat what I said while I'm being recorded. Although I am running out of, looks like I'm running out of time. I hope you don't mind that I'm talking about this stuff during class. So, yeah. Yeah. How you doing, Dan? Am I scaring you? I'm trying not to scare people.
I'm good. Thank you.
All right, but maybe unless anyone has any questions, I'm looking at 25 minutes left. I think I can certainly finish the equilibrium in that time. I could probably do it in 15 minutes. Does anybody have any questions? Okay. I'm sorry, what? Safely. What is it now?
I went to desk for work, and then I checked Facebook first, and they ran out of gas. So the next day, when I actually had to go to work, they only had like 3
Oh, no. Well, what is Costco? I guess. Oh, you don't? Okay, yeah. No, it's, yeah. That's gonna hit us pretty hard. The fuel prices are gonna go high. Because Russia's a major supplier, and the sanctions, it's not just gonna hurt Russia, it's gonna hurt us too. But our economy is just so huge, it's not gonna hurt us as badly. No, I think I told you guys, I used to live in Hungary. Like, did I tell you that? I used to live in Budapest, Hungary. And I mean, the communist culture is very different. Very different. And I mean, I would not want to be under communism. I mean, although Hungary was not under communism, I was there in 2006. But I mean, there was still a bit of the communist culture after the fall of the Soviet Union in 1991. I mean, it's very different. And like, I mean, Putin's having a hard time because the Russians like the Western lifestyle better. I mean, communism, some people love communism. They absolutely love communism. So, but most people don't. I can tell stories. Let me finish this and then we can talk story about communism, or at least the culture. Okay, so this is where we left off, or unless any question, no, okay. So we left off, and so you have this reaction here, 2 hydrogen sulfides in equilibrium with 2 hydrogens and sulfur, diatomic sulfur. Initially 0.025 molar hydrogen sulfide, no hydrogen, no sulfur.
Sorry,
So
could you share screen?
What's that? Oh, sorry.
Could you share
thank you, Dan. I'm sorry. Okay. Okay. So, so you shift right towards product side. You lose 2 extended reactions of the 2 hydrogen sulfides. You gain 2 extended reactions for the 2 hydrogens, and you gain 1 extended reaction for the sulfurs. So equilibrium, the 0.025 initial minus 2 extended reactions for hydrogen sulfide, 2 extended reactions for hydrogen, extended reaction for diatomic sulfur. So set up the equilibrium expression, which we're given the value 1.67 by 10 to the minus 7. So it's products over reactants. So 2x for hydrogen squared times x for sulfur, and that's 4x cubed. And then you have the 0.025 minus 2x for the reactant side, that quantity squared. And I forgot the squared here. This is going to be squared. Squared, and then we're using this x is small approximation because of this term here. We're saying that we can say that x is small, so this 0.025 minus 2x is about 0.025, and we drop that and makes the math significantly easier, and we get x equal to about 3 times 10 to the minus 4, which is within 1% of that value. So it's not that much error, like it's 1-ish% error associated with this calculation. So we were saying that's okay. Again, if you have a sweet calculator that has a solver function, go ahead and use it. If you have access to Mathematica or MATLAB, go ahead, use it. Use a solver function. We're not in the age of slide rules anymore. If you want to use computers, go ahead. But either way, this is a sloppy math trick to get an approximate value, and then it makes our calculations significantly easier. So normally, I'd have you do this, but we're not gonna. I mean, let's just say we don't have time. I'll just go ahead and set this one up then. So we have SO2Cl2 in equilibrium with SO2 plus Cl2. Kc is 2.99 times 10 to the minus 7. If the initial concentration of SO2Cl2 is 0.175 molar. What is the concentration of chlorine at equilibrium? So how do you solve this one? SO2Cl2. I always write the equation out. I mean, I know I should put concentrations, but I just, I usually just put ice, initial change equilibrium. So 0.17500, shift right. So 0.175 minus x, x, x. So equals, it's going to be concentration of SO2, concentration of Cl2, all over concentration of SO2Cl2 equals 2.99 times 10 to the minus 7 equals x squared over 0.175 minus x, which is approximately x squared over 0.175. So that means x equals 0.175 times 2.99 times 10 to the minus 7 square root. And if you do that, you get that. So I know rather than shift your brains out, and you guys have done well for the other ones. So, but does anyone have any questions on how to set those up? Yeah.
So how do you determine a therefore changes negative x, positive x, and positive x?
Okay. So it has to do with do you remember when we were talking about the Q values? So, okay, the reaction quotients. So you're given a reaction quotient, and it's the same thing as the equilibrium expression. It's products over reactants raised to the powers. So, if let's say if Q is too small, so Q is going to be, in this case, let's say Q is small. That means the numerator is too small. And you say small compared to K. So K is Q at equilibrium. If Q is small, that means the top number is too small and the bottom number is too big. And that means that you need to generate more of the top number and you need to lose more of the bottom number. How do you do that? You shift right. You shift right towards the product side. Okay, say it's the other way around. Say that Q is too big. It's bigger than K. That means this number is too big and this number is too small. What do you do in that issue? You shift left. And in this case, you have zeros. You have no products. So you have to shift towards the side of products. That's the only option. There's no products. So shifting left just can't be an option. You have to shift right. You can only shift right. And these plus X's and minus X's, because I'll change colors to pink, there's always emphasized there's one of everything. So that means that you're going to lose one extent of reaction, how far the reaction goes of the reactants, and you're gaining one extent of reaction for each of the products. But if you compare that to here, you have a 2 here and a 2 here, a 2 here and a 2 here, and a 1 here and a 1 here, right? Because you have 2 units that side and two units H2S, 2 units H2, and 1 unit S2. Make sense? Usually there's zeros. If you look at this problem, there's a 0 in the reactant side. So in this case, you shift left because you have no reactants in some products. So you shift the other way. So, make sense? Okay. All right. Last thing I want to talk about, and to be honest with you, this is probably the most important thing you can learn this semester. And this works for, it works for more than just chemistry. Okay, so it's not, it works for everything. Or at least you can apply this process to everything. Le Chatelier's principle is equilibrium shifts to counteract a change. So now, let's say, you know, the price of gas goes up, bread gets really expensive, and I lose my job. Okay, does that mean I'm going to go out and buy a new car? Right? Am I like, you know what? I think it's a good time to, you know, buy that Corvette I've always wanted, or, it's time to take my, pandemic's almost over. It's time for me to take my dream trip to Kiev, kind of thing. So does that mean that, if I suddenly have a huge loss in income, I'm gonna start spending things lavishly? Say, no, of course not. I mean, I'm used to living a certain way, and if suddenly I have a huge loss of income, I'm probably not going to start spending. Some people do. I just watched whatever it is, Inventing Anna on Netflix. I saw her spending money she didn't have. But most people respond to a loss of income by being a little bit more frugal, right? You're going to start watching more Netflix movies at home and eating crock pot meals, not going out as much. You're going to try and stretch your money as thinly as you can, right? So what's going to happen if you win the lottery, though? So go in. So I know we don't have a lottery here in Hawaii, but say you're in the mainland and you get $100 million playing Powerball. Are you going to be like, yep, well, time to eat more Kraft dinners, time to stay home, watching Netflix? No, you're going to start spending lavishly, probably. You're going to, so, do I really want my 20-year-old Toyota Corolla? Maybe, I'll buy a Tesla, kind of thing. So if you have a sudden influx of money, you're probably going to spend more money, kind of thing. So that's a shift in equilibrium. So same idea with chemical reactions. So same thing with reactants and products. So you have these reactants in equilibrium with products. What happens when you add more reactants to a system? So you have a vessel and it's equilibrium, and we add more reactants. The system has too many reactants, so it shifts to counteract the change. It consumes more reactants, and you shift right towards the products. So in adding reactants, you shift right. If you remove reactants, it shifts left. So if you remove reactants, you shift left and you form more reactants. So with systems at equilibrium and you take away reactants, the system wants to form more reactants, it forms more reactants. Same idea with products. If you increase the amount of products in your system, you shift left to get rid of the products, you shift towards the reactants. If you decrease the amount of products, you shift right to form more products. And of course, this is very important. Decreasing the amount of products to shift right. So they do this with ammonia synthesis. So making ammonia, you have ammonia in equilibrium with hydrogen and nitrogen. You remove ammonia, and then you throw this stuff. Then you put it back into the vessel, and it shifts right and forms more products. Okay. Does anybody have any questions so far? Okay, what do you do for catalyst? Say you have a system at equilibrium, you add a catalyst, what happens? Absolutely nothing, at least for Le Chatelier's principle. The equilibrium does not shift. You have the reaction goes faster, but the equilibrium does not change. So for heat, so if you look at exothermic reactants, you can look at heat as being a product. So if you add heat to an exothermic reaction, so you're adding a product to the reaction, you shift the reaction to the left. For endothermic, heat is a reactant. So adding heat or increasing the temperature to an endothermic reaction means you shift right towards the products. So, and the opposite is true for taking away energy. So for an exothermic reaction, so you take away heat, you're taking away a product. That means you shift the reaction to the right. If you take heat away from an endothermic reaction, you shift left towards reactants. So, does that make sense? Now, what about moles of gas? So we have nitrogen and hydrogen in equilibrium with ammonia. I talked about that before. I mean, this is used for ammonia synthesis to make fertilizer. And very commonly, you have the reaction vessel and you compress it down. It compresses out the ammonia, and then you take away products, you shift right. So that that's how you clear it out of the vessel for making ammonia. But you can think of, if you look at this equilibrium though, you have 4 moles of gas on the left, and you have 2 moles of gas on the right. So I think of it in terms of volume, and so the system changes to counteract the change. So if you increase the volume, so if you increase the volume, the pressure goes down. So that's Boyle's law, right? Remember, so volume goes up, pressure goes down, right? They're inversely proportional. Volume goes up, pressure goes down. So you increase the volume, the pressure goes down. The system wants to increase the pressure, so it wants to stay the same. How does it increase the pressure? It shifts to the side of the more moles of gas. So there's 4 moles of gas on the left. So decreasing the volume, you shift left. And decreasing the volume is increasing the volume is the same thing as decreasing the pressure, which you also shift left. What about lowering the volume? If you lower the volume, you make the system more pressurized. The system doesn't want to have that much pressure. It shifts to the side that has the fewer moles of gas. So in this reaction, decreasing the volume, the same thing as increasing the pressure, it shifts right towards the lower moles of gas. And so remember, the system is counteracting the change, whatever you're doing, right? So if one of you darling students were to come up and push me, if I didn't want to fall over, I have to fight you in the direction that you're pushing me for me to stay balanced. Same thing with the system. So that's Le Chatelier's principle. So the system is changing, is shifting to counteract the change. And so it's going to change by the volume and pressure in that way. So what about if you have the moles on the other side? So if you have SO2, Cl2, 1 mole of gas on the left and 2 moles of gas on the right. So this is going to be opposite. Increasing the volume is the same thing as decreasing the pressure. So you shift right to try and form more pressure. If you lower the volume and you up the pressure, in this case, you shift left towards the lower moles of gas. So, and if you have something like this, where if you have 2 moles of gas, if you do the same on both sides, increasing the volume, decreasing the volume, increasing the pressure, decreasing the pressure, you can do absolutely nothing. So there's nothing will happen in that circumstance. So questions? If you have the same number of moles of gas on both sides of the equation, changing the pressure and volume is going to do absolutely nothing. The equilibrium will not shift at all. It's only when you have a difference in the moles of gas in a equilibrium that it matters. Okay, so let's look at this equation here. 2 hydrogens plus oxygen in equilibrium with water. I should say these are all gas. And this is an exothermic reaction. What's going to happen when we add hydrogen reactant? Are we going to shift right, shift left, or no change? So adding a reactant is going to cause the system to shift right towards the products. What's going to happen if we remove water product from the system? We are going to shift right towards the products to generate more products. What's going to happen when we take away temperature, take away energy from this exothermic reaction? It's exothermic, so that means that energy is a product. And if we remove a product from the system, which direction are we going to shift? We are going to shift right. Correct. What's going to happen if we add a catalyst to this reaction? Say we do it under platinum, that's a catalyst. What's going to happen to the system? Absolutely nothing. No change. What's going to happen if we decrease the pressure? So decreasing the pressure means that the system is going to want to increase the pressure. And we have 3 moles of gas on the reactant side, and we have 2 moles of gas on the product side. So what are we going to do if we decrease the pressure? It's going to shift left. It's going to shift left towards the side that has the more pressure or the more moles of gas, because the system has more room. It's going to kind of like if you're feeling really fat. I don't know if I feel really fat and I loosen my belt, I feel like my belly flies off. Like, this is I'm no longer sucking it in. I'm letting myself go. That's when the pressure decreases, you increase, just kind of let it all fly. At least your gut, I mean. So, make sense? And these are the kind of questions you would get. And again, this is, you can apply this to other things. So this is not, you can apply it to finances. It's Le Chatelier's principle. And it's so easy. And people don't go through this logic very often. So it's funny. And I think it makes so much sense. So questions? So I got 2 minutes left to class. Yeah, please, Dennis. For which question? Yeah, I mean, each one would be a different question. Yeah, it's a column. The first 3 are A, the third one is C, the last one's B. So each one has a different value. So questions? All right. So, and don't worry, I know Dan, you're an ask this, so you can have another week for the test. It's all fine. And I'll start bugging you. But yeah, I guess class is over then. If you have anybody has any questions. Okay, I'll